So today we're going to be using the generic cubic equation of state to come up with a cubic polynomial equation for the compressibility factor Z. So if you remember, our compressibility factor equation is Z equals pressure times volume, where volume is the specific volume, over R times temperature. So to include our compressibility factor Z into this cubic equation of state here, we want to multiply our entire equation here by V over RT so that we get Z on the left-hand side over here where this pressure is. So we multiply by V over RT. I'm just going to go ahead and erase this. We'll be left with Z. And our RTs are going to cancel out here, so we're left with V over V minus V. And then we have AV over RT V plus epsilon V, V plus sigma V. So the next step that we want to do is to get a common denominator. That's our end goal, is to find a common denominator to get our equation into a cubic polynomial state. So to do that, we're going to start with dividing out our right side of the equation here by V. So we'll have 1 over 1 minus V over V minus A over RT. And we can just go ahead and pick one of these to divide B, or to divide V. So I'm just going to pick this first one here with epsilon. So we'll have 1 minus epsilon B over V. Then V plus epsilon B. I'm sorry, that's plus, not minus. So now the reason we're doing this is because we want to be able to rewrite the expression so that it has the compressibility factor in it. In real world applications, you would be given pressure and temperature, and you'll want the specific volume. So essentially, we're making it easier to find that volume by deriving this cubic polynomial equation for the compressibility factor. So I'm just going to go ahead and factor out this V here. So that way we have all V's in our denominators. So we'll have 1 plus sigma V over V. So now we can substitute in with our compressibility factor. So we know Z equals PV over RT. We can rewrite this to say that V equals RTZ over P. So now anywhere we see a volume, we can include this expression for volume, substitute that in. And this way, we're just replacing the volumes with our compressibility factor Z, so we include that in our equation here. So we'll have 1 over 1 minus B minus BV over RTZ minus AP over R squared T squared Z, 1 plus epsilon BP over RTZ, 1 plus Okay, so now that we have replaced all the volumes, we can see that we have similar terms in all of these expressions, the BP over RTZ, Z in our equation, because that's what we're going to be getting at in the end. So we can make a substitution of a new variable, just to simplify our expression, saying that our new variable beta is equal to BP over RT. Then we can go back through and substitute our beta anywhere we see BP over RT. So our new expression looks like 1 over 1 minus 1 over Z. A times pressure over R squared, T squared, Z 1 plus epsilon over Z. I'm sorry, epsilon beta, forgot to put it in there. 1 plus sigma beta over Z. So now we can simplify this down even further. So if we just look at our AP over R squared T squared Z, can simplify that out to say AP over RT multiplied by 1 over RTZ. So if you see, there is a similarity between our beta BP over RT and we have AP over RT. So we can say that AP over RT is equal to A times beta divided by B. Hopefully that makes sense, that algebra there. So then we're left with A beta over RTZ. And here, I'm sorry, A beta over BRT times R1 over Z. And we can simplify this down even further by substituting a new variable. We'll call it, I don't know, Q, and say that's equal to A over BRT. So now we can rewrite our equation with Q and beta. So we'll have, again, Z equals 1 over 1 minus beta over Z. This should be a beta up here. I apologize. Minus our, so our A is now going to be beta times Q over Z, 1 plus epsilon beta over Z times 1 plus sigma beta over Z. Okay, so we're getting closer to finding our common denominator now. So if you notice, we have a lot of Z's in our denominator. We can simplify this a bit more by dividing out Z from our equation here. So we'll be left with, actually, just write that out, divided by Z here. So we'll have 1 is equal to 1 over, now it's going to be Z minus beta minus beta Q over Z plus epsilon beta times Z plus sigma beta. So now we're almost there to getting a common denominator. The first thing that we're going to do this is a little cross multiplication to find our common denominator. So if we multiply this by that, just as a visual for you, we'll have Z plus epsilon beta times Z plus sigma beta minus our BQ times our z minus beta, sorry, all divided by our common denominator, z minus beta times z plus epsilon beta times z plus sigma beta. So I just went ahead and factored out this equation up here to make it into a more simplified version, easier for us to make this cubic polynomial. So the next step that we're going to want to do is multiply out the denominator to the other side of the equation and get all of our terms on one side, set it equal to 0. So that way we can find our a, b, c, and d values for our cubic polynomial. So as a reminder, we'll have a z cubed plus bz squared plus cz plus d. So essentially what we're going to try and do is find the a, b, c, and d values for this polynomial. So I'm going to cut and go ahead and do that and make sure I don't get anything wrong and highlight everything so it'll be easier to see where our terms are. So as you can see, I went ahead and color-coded everything to make it a little easier to find our variables here. So in yellow, we have our z cubed values for a, which is just going to be 1. And then for z squared, they're all in blue here, so we'll have 1. We'll have an epsilon plus sigma times beta. Sorry, this should be a -1 for when we move it over. And then we'll have a negative beta as well. For c here in pink, for just z, we'll have negative epsilon plus sigma times beta. We'll have our beta times q. I think that should not be squared. And then we'll have our negative, I'm just gonna make this as 1. Beta squared. And then we'll have epsilon sigma beta squared. And then our d values is anything that doesn't have a z unit. So epsilon sigma beta squared, epsilon sigma beta cubed, and our negative qb squared. This should be squared. I was looking at the wrong one. Okay. So these values here, this expression is going to be extremely useful for us. And I just wrote it this way because it would be such a long equation to write it out, setting it equal to 0. So this is like a simplified version where you can see what each terms are. And this is going to be really useful in helping us find different volumes in liquid and gas particles for a single substance.